And I would like to introduce to Stefano Lottini. He will talk about vector databases for GenAI and beyond. Why you need one, you should know. Maybe you changed the title, but I didn't follow that. It's fine. And I want to talk about our sponsors today, EPAM. And EPAM is leading the industry in digital and physical product development and digital platform engineering services. Through its innovative strategy, integrated advisory, consulting, and design capabilities, EPAM's globally deployed hybrid teams help make the future real for clients and communities around the world by powering better enterprise, education, and health platforms that connect people, optimize experience, and improve people's lives. No problem. And yeah, I don't want to take more time. Please, Stefano, take the stage and give him a great round of applause, please.
Thank you. It's done. Okay. Thank you for the introduction. Hello, everyone. Thank you for being here, in particular, given the adverse environmental conditions to reach this stage. At some point, I thought the room would be empty because of the flood. But now I hope it rains, so you're locked in for 2 hours with me and vector databases. So I'm Stefano. I work at DataStax, where we do data and AI stuff. I personally work with Apache Cassandra. And I've been involved with making it easier for developers to use Cassandra and other databases for GenAI applications. You're welcome to connect with me. And I'm a bit of an old-fashioned kind of person, so I primarily use email. That's why I put it here, which is counter to current customs, I would say. OK, so today's agenda is vector databases. And it's divided in 3 parts, the first one being covering taking most of the time. The first is vectors and databases. So what is a vector? How could database have to do anything with vectors? Similarities, which turns out to be a huge subject. Then we will have a somewhat shorter part on the main application nowadays of vector databases, which has to do with embeddings and GenAI. And there will be a third part with a bit of a peek inside the belly of the typical vector database, how it works. OK, raise your hand if you are using a vector database in some of your projects. OK, in production. OK, that's good. So the point is that in our company, we've been working a lot with vector databases in the last couple of years. And it's refreshing to meet the developer community at large and realizing it's not a concept that is so commonly used yet as I might think from my special perspective. And with this, I tried to make a presentation that caters to, let's say, newcomers and people who have already some experience. So probably I would manage to disappoint both. Sorry in advance. I will try my best. But first, a disclaimer. This presentation by design is not a GenAI RAG tutorial. So I will try not to dwell too much on RAG. Raise your hand if you know what RAG is. OK, that's pretty good. Anyway, there are so many quality resources specialized on RAG. And I wanted to give you a somehow orthogonal coverage of topics to an extent. OK, so let's start with the first part. This is more or less loosely based on a series of articles I published. You see them here in the insert. The title would be, What We Learned When We Built a Vector Database. And actual customers starting using it, so and so. The actually, the original title was What Not to Do with a Vector Database, because it turns out there are a few standard archetypical pitfalls, which I hope to guard you today against, to save your precious time. Okay, so let's start with databases. I think that a database can be only as good as the kind of queries you can run on it. Is there any? Can I?
Check, check, check.
Can you hear me? Okay, so we're back in business. A database can be only as good as the kind of queries you can run on it. So in the simplest way, you store items in a database by a unique ID, and you retrieve them by the same ID. That's, let's say, the minimum. But then you might want to do something more, like tell me all users who are living in Finland and who signed up before 2015, whatever, and maybe many combinations at once. And then there can be also something a bit more advanced. Let's call them fancy queries. I want all users who mention spiders in their bio, or also when they write it wrong, or maybe users with some of these keywords in their bio, or maybe users who, and then we become more and more abstract, users who have something to do with invertebrate biology in their bio. That's even more, shapeless kind of question. I should say that one of my interests is invertebrate biology, spiders in particular. So you will see some demos here, and some of them are about spiders. Are you uncomfortable with pictures of spiders? Anyway, there are no pictures, just names, so should be good. Okay, change subject, spaceships. I am tasked with writing an application to find the nearest spaceships to my galactic coordinate location. So there are a bunch of spaceships, each has XYZ coordinates. I am at X0, Y0, Z0, somewhere in space. And I need to query my database to find the closest spaceships to me for some reason. I think that's a pretty natural query to run on a database. And yet, it turns out that it's not directly supported by the majority of databases in their, let's say, vanilla shape. And of course, we are not yet at the stage of interstellar travel, unfortunately. But even in a very more mundane setting, this is a kind of query that one might have interest in running. So when I was booking the hotel to come here at the conference, I think the booking website could have really much benefited from such a feature. Find me the hotels, the 5 closest hotels to my target destination in coordinates. Well, probably they have this feature, of course. So let's go back to a bit of a more abstract question, because enlarge your mind. When I say points close to each other, I might not mean points close to each other in a physical space like the one we walk, we move in. So I can think of defining my spaceships by length and width. So I have a space, a 2-dimensional space of shapes. Each spaceship is a point here. And I might run a query to find the spaceships whose shape, whose aspect ratio is as close as possible to my ideal goal. So who said that coordinates in a search should be like meters? Why? Or actually, an actual space I can move in. You can have something more abstract, and it will work if you know the meaning of these coordinates, of course. So after this tiny introduction, let me tell you what is a vector database. It is a database which offers first-class support for this kind of queries. Get me the points as close as possible to this query point in a given space. Which means that in this database, the records come equipped with a vector, like XYZ in my galactic coordinate system, or something. And I have a notion of what it means for points to be close or far away, or better, what it means for points to be similar to each other or dissimilar. And based on this notion, I can run a query, which I will call vector search, find me the rows in the database that are as similar as possible to this query item. I hope the database is able to combine this kind of query with other traditional queries. I want all spaceships close to me which are painted blue, because, I don't know, I have some metadata in my database, stuff like that. So I can hopefully combine queries, vector, and other kind of things. Which brings me to another point. There are some databases that are just vector indices. They just allow vector search. And there are, on the other side, databases which are any traditional database plus a layer that powers a vector search. Sometimes I hear the question, which one is best for me? Which one do I need? So my contention is that just vector is good for evaluation and probably little else, because any reasonable size application will still need to retrieve users by ID, look for users who signed up before this year, and stuff like that. Maybe with vector search. You will see how does vector search enters the picture, but my point is that any application big enough will still be an application we know in the traditional sense. We'll still need to do traditional lookups, queries, analytics, and all that. I just go on, no problem. Okay. So what is... Something happened. I might need a third microphone. It's on? Okay, great, thank you. What is a vector? You have seen it. Most of you probably know that already. Let's say a vector is a notion coming from, well, physics, mathematics, engineering, you name it, a lot of scientific fields. A vector is a mathematical quantity which defines a phenomenon which is not just a number, but it has a direction and a length. So yesterday it was 32 degrees, that's a number. Today the wind is blowing this direction 55 kilometers per hour. That's a vector. So it has a direction and a length, right? Then it so happens that we represent vectors as a list of numbers, like in the other slides, sorry. But that's just an accident, a very useful accident. The concept is that a vector, for me, is an arrow like that. And vectors have a direction and a length. The length is never negative, and they have all sorts of very nice mathematical properties which we don't care about. By the way, raise your hand if you recognize the guy in the picture. Richard Feynman, brilliant physicist, winner of the Nobel Prize, founder of the modern quantum field theory treatment. Well done, you won a prize. I will denote with the picture of Feynman slides which have a bit more mathematical content than the others. Let me just complete this slide saying that if you take all vectors of this kind, for example, with two numbers, they form what is called a vector space, which in that case is just an infinitely wide piece of paper, a plane. And the other thing is that we draw arrows, we think of list of number, but basically a vector can be thought of as one point. So we have an anchor point where all vectors start, and the arrow is the point, the tip of the arrow. That's the vector. That's a way to signal a point in this vector space. Vectors form what is called a vector space, where there are some expectations of behavior, flat behavior. You don't get surprised. You can sum, decompose vectors, and all that kind of linear algebra things. Let's say they are flat. They have no surprises. And then, as we mentioned, there are vectors of 2 dimensions, which means they have 2 numbers in their list, 2 components, and they form a plane. there are three-dimensional vectors. We are all familiar with 3D space, right? If we weren't, we would be, I don't know, bumping into each other all the time, but we don't, because we know very well three-dimensional vectors. Now take all vectors of length 1. So you anchor your vector in a point. They are all of length 1. What kind of points, what kind of surface they cover? A sphere. And that's very important. Out of all the vector space, which is an infinite 3D space, the unit radius sphere is important for vector databases. It's important for your application. I argue that except very rare cases, this is where your application has to live. Period. But this picture is in 3 dimensions because we can see it easily. Rest assured, there are vector spaces with 5, 10, 15, 1 billion, any number of dimensions. The only problem is that it's very hard to draw them, but still, think of a list of 15 numbers. That's a 50-dimensional vector which lives in its own space and everything. That being said, it's not true for our purposes that any list of numbers is a vector. You need some notion of being able to rotate the vectors meaningfully in this space. So let's say I am building my e-commerce, and for some reason I decided to associate to each item a price in dollar and an average rating 1 to 10. I could say, okay, that's a vector. Now I want to implement a feature, similar items. There's a mousepad, 10, 10, and then there is a paperweight, which is 5 rating points away, and there's a t-shirt, which is $5 away. What is the closest is, I don't even think it's a reasonable question to ask. Mathematics alone cannot answer, let's say. So you need to be able to compare dimensions for that to be a vector in a useful sense. So be aware. Now, armed with this mathematical knowledge, let me summarize vector search for databases in a picture. I have a purple query vector. The orange arrows are the rows in my database. Vector search is a feature of the database that tells me the arrows in increasing order of distance or decreasing similarity to the query. That's it. Now, how to make that work is another problem. And let's move a bit on databases. You know, it's ancient history now that there are various flavors of databases. There are relational databases with honored and very well-known history. And then there is a whole family of newer, well, maybe not so new anymore, 15 years or so, newer databases which fall into the category of NoSQL. Whatever that means, it probably just means the databases that people call NoSQL because they have scarcely any other trait in common other than they try to overcome the limitations of relational. And there are graph databases, schemaless, key value, time series, you name it. Today I concentrate on tabular or row-oriented databases, in particular Apache Cassandra. Raise your hand if you know Apache Cassandra and you don't fear it. Yes, I know. It has a bad reputation. Well, I love Cassandra. It's admittedly a bit hard to properly operate because it's a heavy monster designed for heavy workloads. It's a giant. It's able to work with huge amounts of data. It is just like a very complicated piece of machinery with a lot of knobs and a lot of possibilities to shoot yourself in the foot, to misuse, to misconfigure, and everything. It's very hard stuff. But if used correctly, it is the solution for your big data, your web-scale petabyte problems with data. It is able to scale arbitrarily to thousands of machines because it's distributed. And it's distributed in a way that is, there is no master node. Every node can do everything, which makes it very resilient. A good third of the nodes can go down and you will still have no downtime in your application, thanks to various technical implementations which we are not going to see today in detail. One deserves a mention, it's partitioning. So data is partitioned across the nodes, which is not the same as sharding. So data is partitioned in a way that every query knows which nodes to go for this data, which means that regardless of how many nodes are in your giant cluster, query times are constant time, which is important. So just to give you an example, this is a slide from the latest ApacheCon, and this is Apple, the company Apple, mentioning that they are using a Cassandra database for hundreds of petabytes of data, millions of queries per second, and a few other interesting numbers. So Cassandra is a database for very big data. So building on Apache Cassandra DataStax, my company, has built a database called AstraDB, which is sharing the same technical advantages as Cassandra, and is database as a service in the cloud. So you don't have to deal with operations. You click a button, get your database, and start using it, and you reap all the advantages of a heavily distributed, resilient architecture. I mentioned that mainly because you will see some demos later, and out of convenience, they will be running on AstraDB. And so will you be able to as well, because I will share the link, you will be able to play with the demos and do whatever you want. So let's move on. Now I have a question. What is the vector closest to A in this picture, except A? Who says C? Who says B? Who says it depends? That's very good. The answer is, it depends. I actually had planned a prize to the person who would say the answer, but too many of you raised your hand, so we will find another way to give the prize. So the answer is, according to Euclidean similarity, it is C, while according to cosine similarity, it is B. So this was a way to introduce the next important point. Feynman again. So you remember when I said you need a way to properly define what it means for two vectors or 2 points to be similar to each other. Turns out there are two main definitions which differ to different definitions of similarity. And for me, similarity means closeness, and it's the opposite of distance, roughly. So there is a similarity called Euclidean. It's defined here, and it's based on the Euclidean notion of distance. And then there is a cosine similarity. Now, if you like formulae, don't pay attention to this 1 and 2. It's just, uninteresting normalization stuff. The point is that it's based on the dot product divided by the norm of the vectors. We will see something better later, but these are the two main similarities one can use in vector databases. There is more, and we will come to that more later. So similarities. Euclidean similarity is the opposite as Euclidean distance, which is what you get when you take a measuring tape and you just measure the length between the two tips of the arrows. More length, less similar, as easy as that. Cosine similarity measures the angle between the two vectors. Now, this picture is two-dimensional, but this holds in any arbitrarily high dimension. So the smaller the angle, the more similar the vectors. And this is true for the cosine similarity, regardless of the length of the arrows, regardless of the norm of the vector. It's just the angle. So cosine looks only at the angle. Now, a practical word of caution here, because my point here is that there are no established conventions when it comes to vector databases, and you might get lost in the fine print easily. So if you look at the Euclidean distance as a mathematician would define, this is it. And this is what Cassandra and AstraDB and many other databases use. And then they build a similarity out of it, which is 1 over 1 plus delta squared, whatever. So it's a number which neatly goes from 1 for identical vectors to 0 for very far away vectors. All good, all nice. But for example, if you look at another popular database, ChromaDB, for some reason, its notion of distance is actually a square distance. Well, for some reason. The reason is clearly to have less computation. Who cares? It's just a number. But it's not meters. It's square meters for some reason. And likewise, I just told you not to pay attention to this. Actually, you should pay attention. Just be aware of the fact that these numbers are here just so your similarity is, again, 0 to 1. 0 is most dissimilar, 1 is most similar. But if you are a mathematician, you would question these numbers, and actually you would go for what, for example, Wikipedia says. And there is no right or wrong here. It's just a matter of conventions. But the Wikipedia convention is this one. So similarities are from -1 to +1. Actually, this is better illustrated here. So it's small differences, but it can trip your application if you don't pay attention. So here you have two equally oriented, orthogonal, and then completely opposite vectors. And in one case, the scale goes from 1 to 0. In the other, goes from 1 to -1. Just be aware of that. There are even databases that define a cosine distance, which is something like 1 minus this thing, so that the distance increases where this decreases. But that's, again, an arbitrary construct. Just be aware of the fine prints. So back to vector search. What would be a way to implement this kind of search? Find the k vectors most similar to my query vector. If I have any hope to do that exactly, then I have bad news. One idea would be, OK, you could just loop over your database, calculate all similarities, sort, and take the top. That's, of course, not very good at scaling. But even most of the optimizations you can think of would not survive the test of high dimensionality. So let's say you want to do something that on a geographic map would work. You divide in blocks, and wherever your query vector is, you limit your search to 5 squares. That one plus maybe the neighbors, or even 9 squares. But if you are in 20 dimensions, you don't have 9 squares, you have a lot. You can do the calculation. It's an exponential, because you also have the corners, right? All possible corners. So that's what is called the curse of dimensionality. And the gist is traditional vector search, exact vector search algorithms just don't survive beyond 20 dimensions or so. And it so happens that modern AI applications of vector search require way more than 20 dimensions. So let's abandon the idea of exact search, and let's consider, what if I can get a huge performance boost with a slightly approximate way of searching? So I can bear the occasional miss in my search, or the occasional false positive in my search. But this time, instead of taking days, my search takes a millisecond. Maybe that's a convenient choice, right? So instead of doing the KNN search, which would be K nearest neighbor search, exactly, all vector databases in practice implement ANN, which is approximate neighbor search, approximate nearest neighbor search. And these are usually graph-based algorithms. We will come to that much later. And they basically trade accuracy for speed. And it's not like a 2x factor. It's between you cannot run any application to you can run it in milliseconds. So that's an unavoidable kind of compromise. OK, so that being said, we have a demo. I guess you will have access to the slides, and you will have access to all these. There is a repo with all demos. Now I'm running a simple one to play a bit with vectors. If you want to scan and then keep that open for later, this picture with the QR code will come a few times, so don't worry. OK, so this is the repo. You see it's GitHub with a few Python notebooks, and all the little instructions needed to run all of them are here, so I will just flash them by. This is DataStax AstraDB, the database I'm going to use. It's very easy. You go here, you create, or you can basically sign up for a free account, click Create Database, and in a few minutes you are ready, good to go. I did that already, of course. So let me move to demo 1. This is just about a bit of practical experiments with vectors of length 1. Vectors on a sphere, which is what most vectors should live. So installing requirements, importing stuff, uninteresting things, database connection secrets, and we will just flash by. So now the interesting part. Here, a function to calculate the norm of a vector is defined and tested. So there is a vector in 3 dimensions here, 3, 6, 2, and it is length 7. I found a Euclidean, Pythagorean quadruple for that, if you know what I mean. The second one is a funny vector with these 2 components. So it's a vector in the 2-dimensional plane. And this is a typical example, 0.98 and then 0.15. This is like that, and it has length 1. So this is a unit norm vector. This is the good kind of vector. Now I go on to define 7 different documents. Each one bears the name of a spider and has a 3-dimensional vector associated, randomly actually. So let me check what is the norm for these vectors. Here, they are all unit norm. Not a coincidence, I designed them to be so. And how did I do that? Well, trigonometry and all that. Now the interesting part. Let me create a collection in the database which is using the Euclidean metric, measuring tape between tip and tip of the arrow. So I create the collection with the goal of inserting these 7 documents and running a vector search with an arbitrary query vector. So behind the scenes in this moment, a lot of things are going on in the database in the cloud. The collection is ready. Of course, it's empty. I insert my documents, whatever, and now I'm running a query. Remember, the vector query is give me the vectors as close as possible to this one vector I give you. This is the closest, then there is this one, then this one, this one, this one, in decreasing similarity order. And if I run that, here we go, Tmarus, Heliophanos, Ivarka, sorry. So I get my spiders back in a given order. This is Euclidean. Now I create a new collection, and I ask it to be indexing vectors according to cosine this time. So the collection is ready. I do the very same. I insert my spiders, and I run my query. What do you see? Some ordering coming back. But if you look closely and you print just the first letter of each spider, it's the same. Sorry, that was a stupid joke. Why? I just kept telling you it's 2 different metrics, 2 different measures, 2 different similarities. How come? Let's go a bit more in detail. Now I'm printing the 2 results side by side and also the numeric values of the similarities. Okay, you can check it's the same listing, but it's different numbers. Okay, back to the slides for the time being. So lessons from demo 1. One is of the typical use that you do of a vector store. Typically it goes like that. You create the table, the collection, the index, whatever, and you specify the dimensions and what similarity definition you want to use. That's defined when you create the data structure, when you create the collection. Then you start putting data in it, and then you start running queries. And you put more data, and you run queries. You put data, you run queries. Maybe you delete data, you run queries, whatever. As a detail, in this case, this database has a very easy-to-use API. It's a natural Pythonic client. And you see, this is aimed at reducing the mathematical and the computational overhead in your mind. You just do stuff. with an easy client. That's always a good. And it's not like that for all vector databases. OK, so now the important lessons from this demo. Cosine and Euclidean, two very different definitions of similarity, gave the same results in the same order. Why? That's because we are on the sphere where everything is easy. Life is easy on the sphere. Because if you have a longer segment, then you have a wider angle. That's always like that. You actually can define a precise equation to map one similarity to the other. And if you don't believe me, then this is for you. Right? OK, you will see it in the online slides. We are not spending time now. Because now it's time to introduce a third similarity. You just got acquainted with cosine and Euclidean. Now it's time to... Wow, that was not planned. All good there? Unexpected stuff happens. OK, so I think I'll continue, if it's OK. Luckily, there is an ambulance there for bandaging, so shouldn't be too much of a trouble. OK, so I've been given clearance to go on. OK, so let me introduce a third definition of similarity, which is the dot product, this one here. And, well, you might notice that it's very similar to this one, except this one is gone, right? You don't divide by the norms of the vector, because why not? So, but wait a second. If we are always working in a unit sphere in vectors of length 1, then dividing by the length of the vectors is divided by 1. So it should be something I can do, I can skip. Indeed, if you work on the sphere, the dot product similarity is the very same thing as the cosine, except for one thing. It has less computation. So every vector store usually has a quick start with cosine. What they should actually do is they should tell you, use dot all the time, because everybody, almost always, is going to use unit length. Is going to use normalized vector anyway. So you have essentially no reason not to use dot product when you do your vector stuff. This is something that a lot of people don't easily. This is a tip that, for some reason, not everyone easily encounters. You should almost never use cosine except for day one evaluation demo. It's just more computation. Why should you? Of course, if you are off the sphere, then good luck, because then dot is a strange thing. You should not use dot, probably, except if you really know what you're doing. There is something on that later. So the point is that on the sphere, life is easy. Not only is Euclidean essentially the same as cosine modulo numbers, but even better, dot is exactly the same as cosine. So use dot all the time. And we go back to demo 1 for the second part, dot. So I create a third collection with a similarity of type dot product. And I insert, guess what? The same 7 spiders with their usual vector as I did before. Now I'm going to run directly side-by-side vector search on the cosine and the dot with the same query. And predictably, not only do I get the same sort, the same listing of results, but also the numbers match, because length 1 dot is the same as cosine. There's nothing against that. Now, just for the fun of it, arachnologists think they are funny. And at some point, they came up with 3 different spider genera, which are each the anagram of the other. Eratigena, Aterigena, and Tegenaria. They are 3 different spiders, and they are just anagrams. So I gave them 3 different vectors, completely arbitrary, and as you might see, absolutely not on the sphere. They are arbitrary length vectors. So we are off the sphere. We are where the lions are. Now I clean up all collections, and I just insert these 3 items in the cosine, in the dot, and in the Euclidean collection. Now, I'm going to run the same vector search on the 3 tables and just see the order the results come. That's just to convince you that outside of the sphere, all bets are off. Because outside of the sphere, they are really 3 different things, 3 different computations. So be careful. But you probably seldom need to do that, to work outside of the sphere. I mean, you should always work with normalized vectors. Now, as a further demonstration, I'm going to prepare the 7 spiders, but this time the vector is, rescaled. This is not interesting. Let me just show the norms. I prepared, now the length of the vectors are just 3 something, 3, 2, 5, 0, 3, some numbers. That's just to show what happens if I empty the collections, and both in the cosine and the dot, I insert these slightly rescaled vectors of arbitrary length. And now I run the 2 searches. You see, even with the rescaled vectors, arbitrarily rescaled, the cosine gave me the same as before, because cosine does not look at the length. It just looks at the angle. So even if this one is longer, shorter, the angle has not changed. I just rescaled the vectors by a constant factor, all components, all numbers. But dot product, his mate, whatever, because dot product is a strange beast if you're not on the sphere. You probably should never use it. Now let me clean up this demo and go back to my slides. Okay, so lessons from demo 1, second part. Dot is to be used on the sphere. I keep saying that as many times as I met customers who were not aware of this very simple performance-saving tip. Of the sphere, no. Of the sphere, now, you will get to this picture later if you want, but the point is that just the similarities do different things on arbitrary vectors. And a good thing that might save you in some cases is that cosine is resilient to arbitrarily rescaled vectors, which you probably should not even use. Now, there's an implication of what I told you. Let's say you have an application where vectors come in of some norm, and you store them in your collection, which has cosine indexing, cosine similarity. And queries also come in as they are, and you just run queries. And then you get results, V1, V2, in a given order. Now, my application would behave exactly the same if I used a dot product collection, and I took the care of normalizing from V to a unit length V, everything I save, and from Q to unit length Q, every query I run. Because if I can switch to dot, because everything is unit length, I get the same behavior of my application, and I probably save up to 50% CPU latency. Happy customers. That's not a secondary point. Of course, this is under the very reasonable assumption that reading is critical. Read latencies are more critical than write computations, and you read more often, which is almost always the case. So tip, use dot. And also consider dot when the raw data comes non-normalized, except for those very particular cases where the length of the vector has meaning, like actual distances in light years between me and my spaceships. Okay. Another thing that I heard a few times is, we wanted to compare different similarities in our application and see which one performs better. That's usually a waste of time, because you've seen, they are the same. They behave the same. Go on a sphere, normalize your vector, and just stick to whatever feels more convenient, dot. Okay, third tip. Do not attribute any philosophically significant meaning to the numbers you get. Okay, you get a similarity of 0.35. It's wrong to think, that's 35% of my ideal whatever. That's just a number. And different databases have different definitions, and this 35 becomes 51, and that it's just doesn't have an absolute meaning. Don't waste your time. And it gets even worse when we speak of text embeddings and similarities in the case of embeddings. Okay, so I have more demos. I'll probably just skim over those to give more time to what comes next. But this is a quick demo. I'm using the spaceport analogy. I define, what I skip is I'm creating a new collection of 3-dimension and Euclidean, because I'm dealing with spaceports in galactic coordinates. But this time, every spaceport has its own position, which is a 3D vector, but also some metadata. So whether it has a restaurant or not, what is its average user rating, and stuff like that. So let me insert this. Oh, sorry, I skipped one cell. Let me insert these 3 spaceport definition. They are documents. I write them in my database. Now, I am located at 0, 10, 50 galactic coordinates. And I want to see what is my closest spaceport. So you see, I run a find one on my location. Simple vector search. Good. Betelgeuse Bay. Nice. Now I want one with a restaurant. So I do something that I hinted at the beginning. Vector search plus filtering on the metadata. Will it work? Luckily, this is a good enough database, and it supports this kind of hybrid query. But of course, the result is another one. Now I want a spaceport with a high enough rating, and yet another one comes out. Or then I start to get, so you see, sorry, I was too fast. So now my query has a vector and also some metadata condition here. Now I do more. I want 2 conditions and a vector similarity. No matches, too bad. So that's a very simple thing just to show. You can think of what is the power of this combined way of querying in a single database, in a single operation on the database. You can do really big things now. And now this is a bit of a creative usage of vectors. It's nothing new, but it's probably fun. I love philosophy as anybody, but I acknowledge that philosophers' names are sometimes very hard to spell. Schopenhauer, Heidegger, Martin Löw, Wittgenstein, you name it, right? So why shouldn't I build a machine that is a search engine for philosopher names with spell correction? Of course. Some of you might think, Levenstein distance. Yes, that's a possibility. And of course, there are commercially better possibilities, but this is a vector demo. So what I do is I normalize the philosopher name. Let me quickly run through the cells. I create a basis of 676 diagrams, AA, AB, AC, ZZ. Each one is one direction in my 600-dimensional vector space. So except some normalization, which gets me rid of dash, umlauts, and so on, what I do is I reduce every name to a list of contiguous pairs of letters, and then these become vectors. So every time there is AA in my philosopher name, there is a non-zero component in the first number. So you see that Kierkegaard here, which happens to contain an AA, and I swear this was random, then I kept it because AA is useful, is a non-zero first component, AA, then AB, AC, and then there is AR. So this is a vector representing
the philosopher name. Now what happens? It so happens that if I spell something a bit wrong, probably I would get a vector that is close enough to a real philosopher. And then I'm able to tell my customer, maybe you meant Kierkegaard. So let's see if this works. I create a vector collection with dimension 600 whatever, dot, because I normalized the vectors, because I just learned from my past mistakes. And then I have a list, actually very short, list of philosopher names. For each one of them, I calculate its true vector. I insert that in my vector database. Then, okay, let me skip a few things. Okay, so this is the function that does the lookup. But what I want to show you is that whether you spell it right or slightly wrong, you see, this is not the real way to spell Wittgenstein, but still, it works. So Martin Löw, same thing. Mio cugino, no match. Okay, that was too far. Because I set a threshold, and could be something to say about thresholds, but let's just move on. So there are, I hope this convinced you that there are legitimate creative usages of vectors which are not necessarily vector embeddings, which, of course, take the stage in these times. Okay, so actually there was a demo number 4, which I will skip, and I will leave as an exercise for the reader. Let me say, the point of demo 4 is just that I just told you that it's usually not a good idea to just shoehorn different quantities into a list of numbers and call it a vector. Price, rating, that doesn't really work. But there might be cases where you can normalize them into comparable quantities, and you can more or less have something that works. So if you know your prices go from $0 to $10, and your rating goes from 0 to 10, you can divide by 10, both numbers, and you get something that is in the 0,1,0,1 region. So there maybe you can still recover some useful application from looking at similar things to whatever. The rest we saw live. Okay, so this is the part that I love most, and it's the most useless. So I will go quickly, and I hope to pique your curiosity. Dot is a strange beast. That should be now clear, but the point is that if you look at what dot does, and you take some example vectors, you notice that dot product is projection. So this is the query vector, and this is my eratigena, terigena, tegenaria, the 3 anagram spiders. Dot product, for each one of them, takes the projection on the direction of Q. So it's like turning a light here and looking at the shadows. And that makes for a very strange thing to happen, because I guess all of you, when you think of stuff that is far away or close, you all have an implicit expectation, which I call triangle expectation. And that's a watered-down version of what mathematicians call Schwarz inequality or triangle inequality. Let's say I tell you that my house is close to the lake, and I also tell you that the lake is very far from the mountains. So you, in your mind, you know that my house is far from the mountains, right? With dot product, this is not always true. So dot product plays tricks on you. And the reason is best illustrated with pears and rabbits. Because if you dot vectors with a third vector, it's like taking the shadow, right? The projection. But now, are those two things close or far away? If you turn on this light, they are close. And if you turn on this light, they are far away. Or if you want to look at it in a more mathematical way, the notion of close or far away depends on the vector you dot with. And that's tricky, because one of the consequences is that you cannot reliably build a well-working vector index in a database with dot, period. The only case you can is when you work on the sphere, because you can assume dot is the same as cosine, and cosine behaves well on the sphere. I mean, cosine behaves well everywhere, but dot is cosine only on the sphere. So a dot index is not optimized to work everywhere in space. And that's a pity, because you could invent very creative usages of dot outside of the sphere. And with small amounts of data, they work and they are pretty funny. But probably they would not scale very well, because dot is not optimized in vector databases for off-sphere behavior. Yeah, this is a way to illustrate my point, which we will skip, because it's not really useful in real life, I guess, but very funny. So okay, I'm just telling you what they do. By hackish use of dot, you can build this very nice feature of sort your items in the database by arbitrary values. So you have, it's like these soccer games of the 90s. You could sort your players by agility, speed, aim, whatever. So with dot, you can do sort by arbitrary values, or even combination of values. Like, I want to sort by 30% agility and 70% speed. That's something you can do with dot. Or you can also implement multi-vector similarity. So I want to sort my vector for lambda times similarity with vector 1 plus 1 minus lambda similarity with vector 2. I mean, very funny things, but too bad. There are a few spiders in those demos as well, as you see from the tiny image. Okay, so dot is strange, weird. You probably should not use it outside of unit norm vectors unless you did your research. It's a pity because it's funny. Okay, so before closing, let me just mention that there are other similarities in existence. The so-called L1, which sort of looks at ladder-shaped distances, and L infinity, which looks at just the maximum distance over a single axis. They are not relevant for vector databases. They are mostly used for optimizations problems, and they don't have any nice mathematical property, except maybe sometimes helping convergence of algorithms. The point is that they are not friend with rotating vectors, so not very easy to reason with. And the same goes for other ways to quantify similarity. Hamming, Jacquard, Levenstein, they are not really made for numbers, I would say. So let's move on. And did I skip a slide? No. Okay, so to wrap up, this is something that there are, let's say, 3 different similarities, and you can work on the sphere or off the sphere. Please, go to the sphere, use dot, and be happy. If you really cannot, that's just because you want to use Euclidean, because the distances are meaningful. In all other cases, you are probably doing something suboptimally. Okay, demo 7, to close this chapter. This is the longest chapter. Demo 7 is an example, partially adapted from real life, of migrating an application. So let's say you have an application designed to work on a given vector database, and you want to make it work on a new database. In this case, for no particular reason, I started with a ChromaDB running application, and I want to have it run on AstraDB, 2 very legitimate vector databases. This is a short demo to highlight one point, which is there are no established standards. See. Demo number 7, migrate. So, I might try to make everything small enough to fit. This is the application. It's very simple. It creates a ChromaDB vector collection with cosine. It writes 3 vectors in it, which, looking from your perspective, I call 3 o'clock, 6 o'clock, 9 o'clock. With obvious meaning. And then I will query with similarity with 3 o'clock. So I expect this one to be as the most similar, this so-and-so, and this very dissimilar. And the application, you see, runs the query, and then loops through the results. And if they exceed a given threshold, it says, no, too far away. It's a very simple application. It's representative of real things, but of course it had to fit in one slide. So here you see the results. Predictably, 3, 6, 9, this is the closest to my query vector, a bit less, even more, even far worse. Okay, no, but you see here, this is not a similarity. It's increasing as you get far away, and it goes beyond 1, so it's something. It turns out it is that Euclidean distance squared, which Chroma has. And if I didn't read the fine print and all definitions in the documentation, I would have been tripped up when migrating. Now you will see. So this is the same application. Okay, this is the uninteresting part of getting the database secret. Now, the application on Astra goes like that. Creating the collection, of course, it's a slightly different command. But the concept is the same, cosine, specifying cosine. Then I insert my 3 clock positions here. And this is the interesting part. The interesting part is that I have to translate the threshold into a threshold compatible with the numbers coming from Astra, because I read all the documentation. There are no established standards. Not only that, but this is a threshold on similarity. This was a threshold on distance. So when one grows, the other decreases. And my lower than condition becomes a greater than, which is a terrible bug if you don't pay attention to it. So if I run this one, I hope I will get the same results. I do. There is also, as a bonus, a back translation to the Chroma values. But you see, 1, 0, 5, 0. Similarities. Okay, let me clean up. Okay, so that was a very simple demo with, you see, highlighted all the differences, which I told you about. And that's just to scare you a bit. Over the course of preparing this demo, I took the chance to map all possible ways of defining similarities and distances that I encountered, and all ways to translate between each other. So if you look at this, you will notice that there are a lot of combinations. And if you want to migrate an application, you should be aware of there being no standards around. Okay, so that was it for the first and longest part. And that was by design the longest because, as I told you, this is not a RAG tutorial. But still, question, what is the most talked about application for vector databases today? I'm sure you know the answer now. Who said search? That's correct. Who said GenAI? That's correct. It's what is called, well, GenAI in particular, RAG. So RAG stands for Retrieval Augmented Generation. And in its usual way, in its usual shape, it is made by 2 components. Vector search for retrieval and LLMs for the rest. Now, you remember when ChatGPT came out and took the world by storm, we all spent a few weeks or months playing with ChatGPT and having it tell you stuff, answer questions about anything, coding, spiders, anything. It was very good, but of course there was something that it did not know. Because LLMs, as we came to realize a bit after that, LLMs are best at reasoning, at combining text, not at knowing things themselves. So the realization dawned on us all that the best way to use LLMs is to use that as a thinking machine decoupled from the source of the information. So here's the RAG flow, typical, archetypical RAG flow. There is a request coming to my machine. So what is that makes Uloboride family stand out among all the other spider family? Do you know that? It's written there, here, anyway. So the LLM, let's say it doesn't know it. It doesn't know the answer, but that's okay, because the LLM task is to reason. Information is written somewhere else. So the RAG flow goes like that. Starting from the question, I use this question to retrieve relevant facts out of my big bank of facts, of pieces of text containing a lot of information. The relevant ones are fed to the LLM with a prompt. You are an expert arachnologist, and you want to answer this question based on this and this and this. And then the LLM gives out the answer. Uloboride have no venom glands. Nice. I spotted 2 this morning coming here in a bush. Okay, so this is the RAG pattern, the paradigm of how, you remember this chat with your PDF applications that we saw blooming at some point. Of course, the LLM did not know your PDF, but still the application worked because of RAG. To be honest, RAG is based on having an LLM combine these facts into the answer. You can also have a RAG flow without vector search. You can have any other way of retrieving the relevant pieces of text to feed it. But in practice, it turns out that vector search, in almost all cases, is the most powerful way to retrieve relevant information out of your sea, your giant sea of data. So this is RAG. This is not a RAG tutorial, so if you are an expert on RAG, please pardon my sketchy illustrations. And now we came to the point, which of course is the missing link here. You have seen vectors of 2, 3 dimensions made by hand and stuff like that, and then I suddenly start speaking of retrieving relevant pieces of text with vector search. The missing link is here. There is something called vector embeddings. Actually, there is something called embeddings, which is coming from the technology of transformer architectures, these new neural networks which conquered the scene in the last 5, 6 years. It turns out that there is a very useful way to convert, for example, text into vectors, or images, or sounds, or ways to walk. A lot of things, but let's say text. There are models that are capable of converting any text into a vector, but not any vector, because these are sort of, it's a loose conversion, but it retains a very important property. Pieces of text that are very similar in meaning end up being vectors that are very close to each other. So, the hard problem of similarity in meaning, semantic similarity, is mapped to a more tractable geometrical problem. So looking for sentences that more or less have the same meaning or speak of the same thing becomes looking for vectors that are similar to each other. So vector search is the key ingredient in the RAG flow you've just seen here. So how do I fetch the right facts to feed the LLM? I previously made all of these pieces of text into vectors. I make my question into a vector, and I run a vector search. And I get back the most important pieces of text to feed the rest of the machinery. So, one thing I find a bit funny is that at the beginning, vector embeddings were somehow hidden inside the architecture of transformer neural networks. They are sort of a waste product, in a sense, because they were somehow buried inside the inner states of this machine. And you remember these very suddenly effective translation machines. There is a sentence, something happens, and you get the translation. Wow. Suddenly became much more powerful than they used to be. Well, in the belly of these transformers, there were these things that at some point people started to pay attention to as a thing in themselves. And today they are the thing that is sold by the kilobyte, by OpenAI, for example, by many services. These are the things being sold by web services offering embedding models. So they started as a waste product. Reuse, recycle, you know. So the point of vector store coupled with vector embeddings is that they are a very effective machine for information retrieval. So I'm not saying that this is going to supplant any other information retrieval technique, but they are very much very effective. And maybe you can couple the two. You can have hybrid search, keyword and vector, or any combination. And with that, another demo. I hope you like this crazy switching. Maybe it keeps you awake. Okay, so this is just a very simple demo to play a bit with embeddings of pieces of text. I'm gonna show you two ways of using embeddings. One is using a Hugging Face model, which is running locally on this very machine. And the other, later, is what probably most people are doing. I get an OpenAI key, and I call the OpenAI web service. I give it a piece of text, and it gives me back a vector for money. So that's how it works. So I have functions, helper function for calculating the norm, maybe. Yeah. For calculating the norm, to normalize a vector, and to calculate a cosine similarity by hand. No big deal, but so here I instantiate the local Hugging Face any embedding model, and this is a good example. So this is the function that gives me the vector from a text. So you see, I call the model, it's a one line. You call the Hugging Face model and you get the vector, but it is not normalized. I want to use dot because I'm a good developer. I learned my stuff. So the next thing I do is I normalize the vectors by hand, sorry. So I have 4 sentences here. One is about a pond and some insects. Then there's something about a plant, plate tectonics, so geology, and the last one is again about insects. So the first and the last are maybe a bit more, should be a bit more related to each other than the others, even though they are all somehow about science. Okay, so by the way, having to play with that makes integration, makes testing very funny sometimes. You have to craft the sentences to get the right behavior in testing. It can get funny in a horrible way. Okay, so I get my embeddings. Now, this is one of the embeddings for the first sentence. It is 0.005, then something, something, and it's 768 numbers. So the Hugging Face embeddings live in a space that has 700 and so components. So it's one of those cases where I cannot really draw a sphere, but I want to live in a high-dimensional sphere, nevertheless. And they have a norm, let's say 1. So they are good vectors. Okay, so this is printing the similarity, the cosine similarity between the first vector, the pond with the insects, and the other, and actually every sentence. So no surprise, at dawn, the pond with itself similarity of 1, because it's identical. But then you see 0.5, 0.5, 0.7. So it is really real what I told you. The embedding model maps similar meanings into vectors that are more similar to each other. So I can really do something with that. The other two are a bit less similar. Now, remember this number for a second, because we are going to do the very same trick with another embedding model, the OpenAI ADA 2, which is maybe not the latest at the point. But so nothing interesting. I got my OpenAI embeddings, and I do the same. So here you see sentence number 1 becomes a different vector, which this time has more than 1,500 components. So 1536 is a number that most people know by heart today, probably, because that's the standard from the standard OpenAI model. So let me do the same trick here. Okay, first sentence with itself, similarity of 1. The pond with the insects versus the other insect stuff is the highest, 0.9. And the other two, 0.88, 0.87, a bit less. So everything similar to the other model, but not very similar. So there's a lesson here. Do not mix models. Do not keep expectations between models. In other words, if you stick to a model, you stay there. You tune your thresholds and you switch model, you throw away your work. let's say. There is something else. This is just a funny thing that, however, managed to trip up one of our customers in production, and also some of our testing. So here, okay, this is cryptic. I'm calculating 40 times the embeddings for the same sentence, calling OpenAI with 40 sentences in a batch. And then I calculated the similarity of the results, of the first results with all others. You see, I get different stuff. That's because there is a slight non-determinism in OpenAI. Now, I have no idea where in its internal architecture this happens, but just be careful. It's tiny, but it might, make your... So you should be aware of that. Some models are non-deterministic, even though hopefully to a very small extent. I mean, you would expect the very same vector come out 40 times. It doesn't. Surprise. Now, this is my favorite thing. I have 5 sentences. The first 2 come from a philosophy text. The third one is like from, I don't know, someone's diary. I made it up. And then there are 2 completely nonsense things, which differ only here. Ba, 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 ba. Whatever. Now, I can take the embeddings, OpenAI in this case, for all of them, which I do here. And then I print a simple table of similarities, all to all. Look. So, okay, I have ones on the diagonal, no surprise. Then the first 2 were the ones from the same philosophy textbook, and they have a similarity of 896. Okay. If you look here, the 2 nonsense are very similar to each other, 0.99. But my point is that so the first philosophy sentence is not its similarity to the other is not that different from the one with the nonsense. How come? So 0.89 versus 0.88, come on, this is 1%. So, in short, what happens is that even though a vector space is a full, unconquered Far West land, every embedding model, to a greater or lesser extent, concentrate their all embeddings into a narrow cone, which is funny, and we have no control over it, but it's just a fact of life. So there is something which I call a cone, and even if you take the most different and unrelated sentences on Earth, their embeddings, a bit more, a bit less, depending on the model, but they will probably be more like this than like this. In other words, the similarity of these 2 things is high, yes, but then the similarity between this something that makes sense and the nonsense is very similar to the one between 2 sentences that are perfectly legitimate and even somehow on the same topic. You see, there's a difference that is barely 2%. So this is strange and funny and scary, but this is how embeddings are made. We have no way to, at the moment, I don't think we have a way to quantify this thing. We take it as it is. Okay. So lessons from demo 8. Do not mix models. Do not expect that related is 1 and unrelated means 0, because then you are off to bad surprises. And expect, so the real thing is that there is a wasteland, and then every of your sentences will be just concentrated in a tiny sliver of the vector space. Except this is 700 whatever dimensional in the real life or more. Okay, to close this part, I do have a full RAG application to show you. But I will just guide you through the most important parts here. This is very well illustrated. You will see a link. This is also part of the OpenAI cookbook gallery of notebooks. and it's about philosophy. So this is a typical RAG application. What happens is that we have a database with a lot of philosophy quotes by various philosophers, tagged with metadata, author, and whatnot. And we have two applications. So in the database, the quotes are stored with their embedding. Then we have a search engine, which works. I will skip everything else in this demo. You can run it yourself and have fun dissecting it. So loading, saving, whatever. So search engine. There is a function called find quote, optionally with author and other metadata. So this is a search engine. You write what looks like a quote. It's made into a vector embedding. It is used for vector search on the database, and the best matching result come out. Or you can have, metadata, author, labels, whatever, to constrain the search. But the point is that this is a search engine, pretty standard thing for embedding stuff. I don't know, we can try something. Of course, it will not work, because demos. Morals and virtue, something that usually philosophers like to brag about. Okay, it works. You see? Something. Of course, this is just the retrieval part. And the full RAG is a generator of new philosophy quotes, which is coming next. So quote generator. Now, there is something more. This is something you've seen this morning in the opening talk. There is something called a prompt. So there is a text that humans craft. It could be, you are a generator of philosophy quotes based on these examples. So there is a template which is going to be filled with the result of the search you saw earlier. And then this completed text is sent to the LLM, which does its magic and comes out with a new quote. So again, let me skip a few things. And yeah, this one. I don't know. Morals, what was that? Morals and virtue? Morals and misery. Okay, so misery may cloud our morals, but it is in the darkest moment that our true values shine the brightest, whatever. You can also specify an author and have the quote be created in the style of Schopenhauer. You can be Schopenhauer with an LLM, but that's no news today, right? So this is just a very standard RAG thing. You're welcome to play a bit with that more. Okay, so, lessons from Demo 9, you've seen it work, so nothing to say. Oh, yes, there is a point. Sorry. This RAG example does a lot of manual things, right? It speaks to the LLM. It prepares the prompt by replacing placeholders with the actual results of the search. Because it has run the search, it has converted the search text into a vector manually. It does a lot of things that you might wonder, shouldn't that be automated? Yes, it should, and it has been automated. This morning, something called LangChain was mentioned. Raise your hand if you knew LangChain before this morning. Great. So, yes, on a higher level of abstraction, indeed, these kind of standard ways of interacting with large language models and vectors have been automated to a large extent by a series of possible frameworks. The most important, the best known is LangChain, indeed. But there is also Llama Index, Semantic Kernel by Microsoft, and a flock of other, maybe more specialized, lesser known such frameworks. There are agent-based ones and you name it. So yes, there are ways to automate this kind of flow. And it is representative of the popularity of vector databases that LangChain, if you look at the page, vector databases integrated with LangChain, you find about 100 different databases. So this is basically all of them sprung up in the last 2 years, less. Basically, most of them. So yes, there is quite a great deal of automation already behind that, even though it's still pretty much in its infancy. I think I'll have to skip this very nice topic of what kind of advanced usages you can do with your vector store. I'm not skipping, joking, very quickly. This is about, if you're clever, you can exploit the particular quirks of your database and have your stuff go faster. So Cassandra, for example, keeps data partitioned by user ID, let's say. So why should you add a metadata and run a very slow query on the metadata when you can directly go and run a local vector search on a single node, gaining performance? That's an example. So that's something that a partition database can let you do. Or there is something called Colbert, which goes beyond embedding sentences and embeds single words, more or less. And then the search is a many-to-many between all embeddings from each document and all embeddings from your query. This is a mess, a computational mess, and requires a lot of storage, but it has great effect on the quality of the results. So there are cases where this is being used. And there are other ways. You can combine knowledge graphs with vector search and have even better, because most of the problems today with RAG is how to improve the relevancy of the search results. The R part, the retrieval part, is the most problematic. Okay, so, well, this is, let me skip this, nothing particular. I'm not doing comparison today so much, just to let you know, there are various dimensions to compare vector databases. Most of them are shared by general comparison of databases. In particular, there is something new, which is here, and I will come back to this point. So accuracy. Since these are approximate searches, you might wonder how accurate is my vector search, besides the usual latency, how much it scales, and how much it costs me, and maintenance, and API friendliness, and whatever. So I would mention this thing that is just came out in AstraDB. That's a pretty nice thing. It is an improvement over the typical pattern. So in the typical pattern, you remember, given a query, I speak to an embedding model, I get a vector, and then I use that vector to ask the database. Now, why shouldn't that be directly made by the database? So if you do your configuration of the database properly, you can directly send text to the database, and everything will be hidden there, which is an improvement in latency, in complexity of your code, and all that. So these is the final shape your vector search has. And you don't see any vector here, which is, wow, you save a lot of headache. So this is landed pretty recently, supported by LangChain already. Okay, so looks like I'm more or less on time. And I will quickly show a few details on what is inside a vector database. So how does this magic vector search work? So we are done with embeddings. Okay, so the general idea is that, as in typical database architectures, special kind of search are enabled by indices, which are not directly the data, but they are additional structures built on the original data. So here's my table, which in this case, I think this is Cassandra, so this is partitioned. This is the actual table with the data. And then there is an index, which is elsewhere, maintained independently to an extent. And it is, let's say it's graph-based. Every time a vector search is run, something happens here, a specific kind of lookup is done here, and then these results are actually pointers to the actual data here. So this is not different than any other index built on top of a table in many databases. So you can have another index. Hopefully you can combine them. So composability. You can run a query with different predicates, including vectors. So there will be something going on here, which at the end goes to fetch the actual data here. Of course, then the challenge is to keep this index structure in sync. And to highlight the independency, conceptual independence of these two things, this is what you would do if you were to use Cassandra manually with the CQL language. Here you create the table, and in a totally independent way, after that, you create a vector index here. You see similarity, dot, whatever. Okay. That is just to set the general thing. Now, there is this important quantity to measure performance. So you are interested in how performant your vector database is. So you can ask how big. So can it handle 1 billion of rows? How does the latency scale in that case? How fast it goes when I have 1 billion rows? These are standard questions. But then there is something new, as I mentioned, how relevant the results are. Because you remember, A and N is approximate nearest neighbor. And I can put up with the occasional miss, the occasional false positive, but I should ensure this is below a given acceptable threshold. So there are some standard definitions of how accurate my results are. We can just look at the plots, the drawings here. So recall is how often, how many of the actual results I should get, I actually get. Precision is how many of what I get is actually good. And then there is something called F1, which keeps both of them at once and penalizes errors on both sides of the thing. So these are standardized metrics for measuring accuracy. And they go hand in hand with standardized data sets for running benchmark between vector databases, or actually vector algorithms. Because so there are a lot of algorithms and variants of algorithms to measure, to compare. So this is, I'm not going into details. This is from annbenchmarks.com. And this is the typical way you compare vector databases. You have a recall versus latency trade-off curve. So here is the recall I want. You remember, recall goes to 1 when every row that I should get, I actually get from my search. And of course, to achieve that, I'm prepared to sacrifice latency and to have less and less query per second. So each curve is a different algorithm, implementation, variant. Let's just keep that as a teaser. Of course, we're not going into details. Something that I want to illustrate in some detail is, I think we spoke about this algorithm yesterday a bit with someone, HNSW. This is, let's say, the prototypical algorithm for vector search. So it turns out every viable algorithm that powers vector search in a database is based on a graph or multiple graphs. That's because everything else is very hard to update when new things happens in the data. So HNSW, hierarchical navigable small words, is based on building a set of graphs which are a selection of all the points in the actual data. This is the actual database with all its vectors. And there are different coarse-grained, more and more coarse-grained representations of parts of it, so that when a query comes, this is mapped to a point here. There is a fixed entry point, and then a navigation of this graph starts. Eager navigation that goes immediately to the closest one here. Then I'm done, I jump to the next level, and I try to see if there is something closer. Yes, there is, here. Then I jump down, here. I go to this point, and then I'm done. And this is my best result. So the query part is simple. It's just go for the next closest point, and then if necessary, go down, go down, go down. That's it. And all the complexity is moved into building this graph. So there are various ways, more and more complicated, to build this graph. But the problem is that this is taking a lot of memory. And then there are new problems, because if you want to index a lot of data, you probably run out of memory soon. And then what you do? It's the problem with databases when they are too big to fit a machine. You start doing distributed stuff. You do sharding, which is inefficient. So there are various, I don't have much time now. There are various solutions. Let me just go to something called JVector, JVector is an engine developed within DataStax and open sourced. It is now powering Cassandra. It is powering AstroDB. It is also powering, I don't remember, maybe Couch, maybe, I don't remember what. Some other applications in the wild is using JVector. JVector is the summation of the state of the art in various respects. So it goes beyond the HNSW paradigm. It has a single graph where the existence of long-range jumps is carefully tuned to allow for a single layer to be used. So there are the occasional small word long jumps and then the local moving. And the point is maintaining this structure as effectively working as possible in the face of updates to the data, because entries can be changed, deleted, inserted. And when you have a graph, deleting an item is a nightmare. So there are all sorts of specialized ways to deal with deletions, keeping everything working efficiently. So there is this fresh disk ANN, which is designed to work under constant updates to the data. And then there are a very important technical thing is product quantization, which is like a codebook-based way of compressing the representation of the vectors in memory for a first rough pass, which is then refined with a very tiny amount of disk reads, so you can spill your index to disk with minimal overhead. All that combined with a distributed solution. So I will just leave it at that and skip the performance. It's awesome. That's the summary, and leave you with some bibliography if you're interested in the algorithmic part. Again, this is all, the slides are online, so don't be scared if I just switch to this slide, cookie policy. I have a prize. This is for you. This is for you. These are chocolate cookies from my hometown. You're welcome. I also should award another set of cookies to those who answered the cosine versus Euclidean. We can open them together, whoever raised their hands, because I didn't notice who was. Too many. Okay, so I think I'm done. Thank you for staying with me so far. Okay, thank you. Shall we have, what, 5 minutes for questions, more or less?
I think it's fine.
Okay. So, yeah. Would you use vector databases for geocoordinates GPS? Yes. Yes and no. Okay, so this is a very interesting question. Let me start with a standard answer. Let me fetch one of my spheres, which are here and there. So here. Oh no, okay, so no problem. No, I will draw with my hands. So the problem of geosimilarity, of course, is of very practical importance, and there are design solutions made to work with that. The advantage is that it's two-dimensional. So even if you break the space into cells, you're still efficiently looking at maximum 9 cells. No big deal. So you can do even standard queries. I know of very efficient applications where no need for vector search, because if you choose the right grid system, you can just map your query point to a grid, and then your search becomes a search into a given finite small number of squares. That's enough. But of course, you can do vectors, and then you can do various things. If you are looking in a map of Budapest, for example, you can do 2-dimensionals, because that's basically a flat plane, and you can do 2D searches. But then, maybe you want to do something fancier. You want to look, I don't know, I use the example of the application Volcano Finder, and then your point is in the Fiji Island, and you want to do long-distance stuff on the surface of the Earth. And then you can go the various approximations. So the Earth is a sphere. Okay, then you have to map every point into a 3D point, because then distances are not trivially xy, because the same amount of longitude is different if you go closer to the pole. So you cannot use naively latitude and longitude. So you can map them to 3D points and use the chord, the straight segment, or the cosine, which is the same, except the Earth is an ellipsoid. So you have success, or you can even end up taking elevation into account and having a very complicated map. But then what's your goal for your application? If it's to find the fastest road, then you throw then all away and do a graph approach, because roads, I mean, what's 5 meters when you have a red light, right? So all in all, yes, I would use vector with caution. And to be honest, there are even better solutions in most cases. There are solutions designed to do GeoSearch. And it so happens that, well, Mongo, for example, has one. And it so happens that AstraDB also does. So it does all of the complicated details internally for you. Actually, it goes to the point, it was shown in a slide, but I didn't have time to. It goes to the point that you insert your data with latitude and longitude, but then you can search it with geodistance, and it will do the hover-scene conversion to calculate the actual distance on a geodesic. So maybe there are, in that case, if you're really serious about your performance and accuracy, you might even go beyond vector search and do a more specialized solution. It again depends on what is the actual goal of your application. Okay, so similarity calculation arithmetic performance change when using GPUs. You mean performance? Well, it depends on the model. Most of the models cannot be seriously used without GPUs, except, well, that's not entirely true. If you want to do large-scale stuff, if you are OpenAI, you cannot do without specialized hardware, because then you waste a lot of energy to do very slow calculations. But for the numbers, I'm not aware. I cannot give you number references for GPU testing, sorry, not my expertise. Then, how can the dimension of the vector DB be determined automatically in an abstract object space? I guess this means, how can you determine the dimension given the model? Because that's what sometimes is needed within LangChain, for example. So, okay, so the dimension of the model is in a sense, it's an arbitrary choice when they designed the model. So they went for a 768 slot of numbers for this internal state of the transformer, and why not? Recently, there are variable dimension models which have their dimension arranged in a way that basically you can cut the rightmost numbers, and still the most significant part of the semantic encoding is on the left. So if you cut them at 10 dimensions, you still get a usable similarity model, although with few lossy encoding. And the more dimensions you keep, the more accurate your representation of the semantic similarity is in metric space. And then there, it is a matter of your balance, performance versus accuracy. But in general, you should not give so much meaning to the dimensions. Each space is its own conventional stuff. How do you define threshold for retrieval? That's an awesome question, and unfortunately, I think the answer is you really don't. So I don't think there is a well-established procedure for defining thresholds universally. My dream is to use an LLM to do measurements and then fit, I don't know, a model to infer the threshold based on the question. But I don't think it's a very tricky thing, because what we humans perceive as the same amount of similarity does not necessarily map to the same distance or the same similarity in numbers. So it might be that when the question is about spiders, relevance is beyond 0.9, but when the question is about houses, it's 0.92. So this is really, again, it boils down to how arbitrary, in a sense, and imperscrutable the embeddings are. I don't think there is a clear way to define thresholds. luckily, when it comes to RAG applications, you better retrieve a bit more, and then you send everything to the LLM, and it will sort out what's useless. So that somehow saves you. If the last step is an LLM, then you can afford to be a bit more, you get in. The LLM will clean it out. Multimodal vector databases. Multimodal came out, and I don't think it really took off so much yet. We actually, we had a bit of a discussion with the LangChain team to enlarge the abstractions in their framework to allow for multimodal as a native thing. I remember the answer was, we are not really convinced yet. So I take them as very knowledgeable people, and that was maybe 3 months ago or so, a bit more. It's possible that, I mean, I'm sure we will see multimodal, but at the moment, I don't think there are yet large-scale. There is not yet need for capturing the abstraction behind multimodal into a framework like LangChain would be, LangChain ++ thing. That's my personal opinion. But again, I mostly work in other fields. Okay.
Yeah, I think that's all.
Thank you.